Today we're going to talk about a quiet revolution that is taking place in the world of processors. A revolution that could forever change the way we think about the chips powering our devices. I'm talking about RISC-V, a completely open-source processor architecture that is challenging giants like ARM and Intel. But what makes RISC-V so special? And why should we care? Let's find out together. The story of RISC-V begins much like that of other great projects that have changed the world of technology. In a university classroom with a group of visionary researchers who looked at the future of computing with different eyes. It was 2010 at the University of California, Berkeley, when three computer scientists decided to start a project that at the time seemed almost utopian. Krishte Asanovich, Yunsup Lee, and Andrew Waterman were inspired by the extraordinary success that open-source software had achieved in previous years. Linux-dominated servers, Apache powered much of the web, and projects like GCC and MySQL demonstrated that collaborative innovation could compete with and often outperform proprietary solutions. These researchers asked a simple yet revolutionary question: why couldn't the same open-source philosophy be applied to hardware, specifically to processors? The semiconductor industry was, in fact, dominated by a few giants who controlled architectures through expensive and restrictive licenses. If you wanted to design a processor, you had to go through ARM for mobile and embedded devices, or Intel for desktop and server computers. There were no truly open and free alternatives that allowed distributed innovation like in software. The name chosen for the project tells a story spanning 40 years. RISC-V represents the fifth generation of RISC research projects at Berkeley, a tradition rooted in the early 1980s. It all began in 1981 when a young professor named David Patterson launched the RISC-I and RISC-II projects, which stood for Reduced Instruction Set Computer. At a time when the processor industry was moving toward increasingly complex architectures with massive and intricate instruction sets, Patterson and his team demonstrated that simpler processors could be faster and more efficient. Over the years, Berkeley continued this research with RISC-III, used in the SOAR architecture of 1984, and RISC-IV, implemented in the SPUR architecture of 1988. Each generation brought new ideas and improvements, but they remained academic projects with limited impact on the real-world industry. When David Patterson, by then a legend in the field of computer science and future recipient of the prestigious Turing Award in 2017, decided to join the RISC-V team in 2010, he brought with him not only decades of technical experience, but also the credibility needed to transform what could have been just another academic project into something far more ambitious. The philosophy behind RISC-V was clear from the beginning: to create a processor architecture that was completely open, free, and designed to last. It wasn't just meant to be a cheaper alternative to existing solutions, but a brand new platform that would allow anyone, from startups to tech giants, from universities to national governments, to innovate without barriers. The organizational evolution of RISC-V perfectly reflects this philosophy of openness and neutrality. In 2015, when the project began attracting industry attention, the RISC-V Foundation was created to manage the architecture's development outside the purely academic environment. This was a necessary step to involve commercial companies and provide structure to what was becoming a global community. But the real stroke of strategic genius came in November 2019, when the organization became RISC-V International and moved its headquarters from California to Switzerland. This move was neither random nor motivated by tax reasons. It was a deeply strategic decision with significant geopolitical implications. By establishing RISC-V International in Switzerland, the founders ensured absolute neutrality for designers all over the world, freeing them from any government regulations tied to a single country. In an era of growing trade tensions between the United States and China, and with the semiconductor industry increasingly at the heart of geopolitical disputes, this Swiss neutrality proved prophetic. Today, RISC-V can develop as a truly global standard without the risk of political tensions between countries compromising technical collaboration. The Swiss headquarters allows RISC-V International to operate with the same neutrality as organizations like the International Organization for Standardization, ISO, or the World Wide Web Consortium, W3C, ensuring that engineers from China, the United States, Europe, India, and anywhere else can freely collaborate to improve the architecture, regardless of their government's policies. This journey from the classrooms of Berkeley to Swiss neutrality tells a story that goes far beyond the evolution of a tech project. It tells the story of how an idea born in academia can become a global movement, and how technology, when it is truly open and neutral, can transcend geographic and political borders to unite people with a shared vision of innovation and progress. A truly open architecture. To understand what RISC-V is, let's take a step back. A processor architecture, technically called an ISA or instruction set architecture, is like the language that software uses to talk to hardware. It's the bridge between the programs we write and the transistors that perform the calculations. In the world of processors, there are several families of architectures. x86, the architecture from Intel and AMD that powers most PCs and servers. ARM, the architecture that dominates smartphones, tablets, and increasingly laptops. PowerPC, previously used in Macs and still present in some industrial systems. SPARC, architecture by Sun Microsystems for enterprise servers. Before going further, it's important to clarify something that might be confusing. When I talk about RISC, I'm referring to the design philosophy of simple and efficient processors born in the 1980s. ARM follows this RISC philosophy but is a proprietary architecture owned by ARM Limited. RISC-V follows the same simplicity-oriented RISC philosophy but is completely open and free. They are both RISC in philosophy, but ARM will cost you millions in licenses, while RISC-V is free for everyone. It's like the difference between McDonald's secret sauce and an open-source recipe. Same core idea, completely different business models. Revolutionary modularity, the Lego of processors. Here's where RISC-V becomes truly revolutionary. Traditional architectures are like all-inclusive packages. If you want an ARM Cortex-A78, you get all its features, whether you need them or not. It's like buying a fully equipped car when all you need is a basic engine. RISC-V instead is modular. It works like Lego bricks. Every RISC-V processor starts with a minimal base set of instructions. This includes only the essentials: basic arithmetic operations like addition and subtraction, load and store from memory, conditional jumps and control flow, about 40 instructions in total. The extensions, additional building blocks. Then you can add only what you need: M for multiplication and division, A for atomic operations, useful for multi-core processors, F for single precision floating point, D for double precision floating point, C for compressed instructions to save space, V for vector extensions, perfect for AI and machine learning. Practical advantages of modularity. Example 1, IoT microcontroller. You only need the RV32i base set. Result, tiny chip, ultra-low power consumption, minimal cost. Example 2, AI server. Use RV64IAF DCV with all vector extensions. Result, performance optimized for machine learning. Example 3, automotive. RV64 iMac with custom extensions for functional safety. Result, a processor tailor-made for the automotive industry. Comparison with traditional architectures. Traditional ARM. Want a processor for a smartwatch? You pay for a Cortex-M license that includes features you'll never use. RISC-V. You build exactly the processor you need with RV32IC and that's it. No extra costs, no wasted functionality. x86. Every Intel processor includes decoders for 40-year-old instructions for backward compatibility. You waste silicon and energy on legacy features. You start from scratch with a clean design. If you don't need backward compatibility, don't include it. This modularity means that startups can build specialized chips without massive upfront investment. Established companies can optimize their processors for specific applications. Nations can develop technological sovereignty without relying on foreign licenses. Innovation accelerates because there are no entry barriers. It's the democratization of processor design. From a student's garage to Google's research labs, everyone starts from the same open, free base. RISC-V adopts some very smart design choices that make it efficient and easy to implement. Let's look at the key ones. RISC-V is a load-store architecture, which means one simple thing. The processor can only perform arithmetic operations on data that is already in its registers. Think of registers as ultra-fast drawers where the processor keeps the data in use. If the processor needs to do math with data in RAM, it must load, meaning load the data from RAM into registers. Second, compute, perform the arithmetic operation using the registers. Third, store, meaning store the result from the registers back to RAM. This may sound like an extra step, but it actually makes everything faster and more predictable. It's like having a tidy desk. You keep only what you need within reach. Floating point instructions are simply the commands the processor uses to work with decimal numbers like 3.14159 or 0.5. RISC-V uses the IEEE 754 standard, which is like the universal language for decimals in computing. This means calculations are accurate and compatible across processors. Programmers don't have to worry about inconsistencies across chips. Math software behaves the same everywhere. RISC-V includes clever technical design features. Bit fields optimized for speed. Instructions are arranged so hardware can decode them quickly using components called multiplexers efficiently. Architecturally neutral design. RISC-V doesn't favor any specific implementation. It works well on both simple and complex chips. Fixed position sign bits. Positive and negative numbers always have their sign in the same position, so the processor can immediately tell whether a number is positive or negative without wasting cycles. Think of these features as the good manners of processor design. They make everything more organized, predictable, and fast. By using RISC-V, any organization in the semiconductor, automotive, or consumer electronics sectors can create custom processors without the expensive licenses associated with proprietary architectures. RISC-V's open-source architecture enables unprecedented levels of customization and innovation, allowing developers to design processors tailored to specific needs. For example, Sci-Fi, a leader in RISC-V adoption, has developed customizable chips for automotive and edge computing applications. Designers can use the same base ISA, from simple embedded devices to massive supercomputers, adapting their solution to market requirements. The open-source nature of RISC-V means the entire architecture can be thoroughly reviewed in the public domain, eliminating hidden backdoors and covert channels. Let's talk numbers, because behind RISC-V lies an astonishing growth story. But these are more than just figures. They are the evidence of a true industrial transformation in progress. RISC-V International counts over 3,000 members across 70 countries. To grasp the significance of that number, let's make some comparisons. The entire ARM ecosystem, after decades of dominance, has only a few hundred licensees. Intel and AMD practically control the whole x86 ecosystem on their own. RISC-V, on the other hand, already has a community 10 times larger than ARM's, and we're talking about an architecture that's only 14 years old. Among these 3,000 members is a remarkable mix. Tech giants like Google, Intel, NVIDIA, and Qualcomm work alongside innovative startups like Sci-Fi, Andes Technology, and Star5. Prestigious universities like MIT, Stanford, and ETH Zurich are involved, as well as national governments from the United States, China, India, Brazil, and the European Union, and even individual developers who are the hardware equivalent of Linux contributors. By the end of 2022, more than 10 billion RISC-V chips had already been shipped worldwide. To put that number into perspective, ARM ships around 30 billion chips per year. But that's based on an architecture with over 30 years of development. Intel x86 ships about 300 million chips annually. RISC-V hit 10 billion in just 12 years from the project's inception. That's an extraordinary rate of adoption. But where are all these RISC-V chips being used? We find them in IoT microcontrollers powering sensors, smart home devices, and wearables. They're embedded in controllers for the automotive, industrial, and medical sectors. They function as coprocessors within larger SoCs for specific tasks, and as AI accelerators for machine learning. Future projections are even more impressive. According to SHD Group, one of the leading semiconductor analysis firms, By 2030, we'll see 16.2 billion RISC-V units shipped annually, with 62% growth over 8 years. Total revenue is expected to hit $92 billion, with a compound annual growth rate, CAGR, of 40%. To understand just how incredible that 40% annual growth rate is, consider that the semiconductor industry typically grows between 5% and 10% per year. ARM, at the peak of its expansion from 2010 to 2020, saw about 15% annual growth. RISC-V is growing nearly 3 times faster than ARM at its height. RISC-V International estimates that the market for RISC-V intellectual property and software will reach $1.07 billion by 2025. For comparison, the total ARM IP market today is worth around $2 to $3 billion. Government investments are massive and global. The European Union allocated €270 million for RISC-V projects in 2023. India launched the National DIRV Initiative, short for Digital India RISC-V Microprocessor. China has a national plan to migrate to RISC-V by 2030. Brazil became a premier board member of RISC-V International in 2024. We are at a pivotal moment. Between 2022 and 2023, we witnessed the preparation phase, full mainline Linux support, mature tool chains like GCC and LLVM, and the first stable Linux distributions. 2024 marked the acceleration phase, with the first commercial RISC-V laptop developed by Deep Computing running Ubuntu, server-grade chips from Alibaba for cloud computing, and announcements of RISC-V processors for automotive applications. Between 2025 and 2030, we expect the real explosion. Penetration into mainstream markets like smartphones and laptops, massive enterprise adoption, and technological sovereignty for many countries. RISC-V's growth trajectory is highly reminiscent of Linux during the 1990s and 2000s. Linux began at a university with Linus Torvalds, experienced exponential growth after 2000, and reached dominance in the server world within about 15 years. RISC-V has followed a similar path. Born at Berkeley, exponential growth since 2020, and potential dominance in embedded and AI sectors over the next 15 years. The difference? RISC-V is growing faster than Linux did, thanks to a mature software ecosystem, with Linux and toolchains ready, immediate industry support, and geopolitical pressures accelerating its adoption. $92 billion by 2030 isn't just a number. It represents thousands of jobs in hardware innovation, lower costs for electronic devices, accelerated development in artificial intelligence, IoT, and automotive, technological independence for nations and companies, and the democratization of hardware design. In other words, we are witnessing the birth of a new technological ecosystem that could redefine the semiconductor industry for decades to come. The alliance between RISC-V and Linux is one of the most promising tech partnerships in recent years. It's not just about technical compatibility, but about a synergy that is unlocking entirely new possibilities in the computing world. The turning point came in 2022 when mainline support for RISC-V was added to the Linux kernel version 5.7, along with its full toolchain. This wasn't just a technical milestone, it was a strategic breakthrough for RISC-V adoption. It means that from that moment on, any Linux distribution based on recent kernels could run natively on RISC-V processors without any special modifications. In July 2023, we saw another fundamental step. RISC-V, in its 64-bit variant known as RISC-V64, was included as an official architecture in the Debian Linux distribution, initially in the unstable branch, with the goal of reaching stability soon after. Fedora followed this path as well, officially supporting RISC-V as an alternative architecture starting in 2025. These are not just academic experiments. They are signs that the Linux ecosystem sees RISC-V as a serious and long-term platform. Throughout 2024, RISC-V made major strides in software development. We're talking about numerous improvements to the Linux kernel and toolchains, new targets enabled for various processor types, and additional supported instructions. All of this work is contributing to a more robust and complete RISC-V software ecosystem. It's no longer a question of if the software will work on RISC-V, but rather how well and how fast. The first tangible commercial result of this alliance came in June 2024, when the Hong Kong-based company Deep Computing announced the availability of the world's first RISC-V laptop capable of running standard Ubuntu Linux out of the box, without modifications or special tweaks. It's a powerful symbolic moment. It means RISC-V has reached the maturity needed to run a full operating system on consumer-grade hardware. It would be dishonest to speak only of RISC-V's successes without acknowledging the real challenges the architecture still faces. Like any emerging technology, RISC-V has its weaknesses, which could slow down adoption if not properly addressed. The most obvious issue concerns the software ecosystem, which is still immature compared to well-established architectures like ARM or x86. While Linux now runs natively on RISC-V, many specialized development tools, optimized libraries, and commercial applications still need to be ported or optimized for this architecture. It's a classic chicken and egg problem. Software becomes available when enough hardware is in circulation, but hardware only spreads when enough software exists to support it. On the hardware side, options are still limited. While ARM and x86 offer hundreds of processor models for virtually every use case, RISC-V's offerings remain relatively sparse. There are excellent processors for specific applications, but the variety and depth of choice seen in mature ecosystems is still lacking. A subtler yet potentially dangerous risk is fragmentation. The flexibility of RISC-V, one of its greatest strengths, could become a problem if different vendors implement incompatible extensions. Imagine a scenario where every RISC-V chip manufacturer adds its own custom instructions. You'd end up with processors that are all called RISC-V, but are effectively incompatible with each other. This brings us to the issue of standardization. RISC-V International is working to define clear standards for implementations, tools, and extensions, but this is a complex and lengthy process. Without these standards, compatibility issues could arise that would affect interoperability and hinder widespread adoption of the architecture. The impact of RISC-V on Linux and the open-source ecosystem goes far beyond the simple addition of a newly supported architecture. We're talking about a transformation that could completely redefine the relationship between hardware and software in the age of open source. Linux has quickly become a central component of the RISC-V ecosystem, and it's easy to see why. Linux developers around the world are actively optimizing and adapting the kernel to run more smoothly on RISC-V processors. This collaboration is not one way. While Linux benefits from a fully open new hardware platform, RISC-V benefits from the maturity and robustness of an operating system tested on billions of devices. The combination of RISC-V and Linux is creating opportunities that were previously unthinkable. We're talking about ultra-specialized IoT devices that can be optimized down to the last transistor for specific applications. Fully customized AI accelerators running optimized open-source software. Embedded systems tailored for industrial, medical, or automotive uses. Servers and data centers with custom architectures adapted precisely to the workloads of each company. But perhaps the most revolutionary aspect is how RISC-V is democratizing chip design. Previously, if you wanted to create a custom processor, you needed access to expensive licenses, highly specialized hardware design teams, and massive capital. Today, with RISC-V and Linux, a hardware startup can get started with relatively modest investment and build custom processors for their specific applications. It's the same revolution Linux brought to software, lowering barriers to entry and enabling distributed innovation. RISC-V applications are no longer just futuristic promises, but concrete realities already transforming various industrial sectors. Let's look at some examples that show how this architecture is making its way into the real world. In the fields of artificial intelligence and the Internet of Things, Alibaba, through its T-Head division, has developed RISC-V-based processors in the Xuanti family, specifically optimized for AI and IoT workloads. These processors are not just technical demonstrations. They're commercial solutions proving how RISC-V can boost performance while optimizing for energy efficiency, a crucial factor for battery-powered devices or those operating in constrained environments. But RISC-V isn't limited to the commercial sector. It is already deeply integrated into the innovation ecosystem of the United States in projects ranging from public to private sectors. At NASA's Jet Propulsion Laboratory, RISC-V is being used for space computing, where reliability and the ability to fully verify the code are essential. At DARPA, the Defense Advanced Research Projects Agency, RISC-V is being used for research into hardware security, leveraging the transparency of the open architecture to develop more secure and verifiable systems. In the world of microcontrollers and IoT devices, RISC-V is gaining widespread use due to its simplicity, efficiency, and fully programmable instruction set. We're not just talking about simple sensors, but complete ecosystems of intelligent devices that can be specifically optimized for their functions, from industrial control systems to wearable medical devices, from automotive systems to smart home products. The success of RISC-V isn't happening in a vacuum. It's unfolding during a time of growing geopolitical tensions in the tech world. This creates complex dynamics that are well worth understanding. Since 2023, China has launched a strategic and massive migration towards RISC-V. But why? The decision is tied to trade wars and potential sanctions that could block the country from accessing proprietary ISAs. Think about it. ARM and x86 are architectures controlled by Western companies like ARM Limited, Intel, and AMD. If the US decided to expand sanctions, China could completely lose access to these crucial technologies. China's response has been to develop a national plan to migrate most CPU and microcontroller designs to RISC-V by 2030. We're talking about massive investments in companies like Alibaba T-Head, which developed the Xuanti processors, and academic partnerships with universities to train a new generation of RISC-V engineers. This is not just theory. Alibaba has already announced the Damo Xuanti C930, a server-grade CPU, and senior executives from Alibaba Cloud have predicted that RISC-V will become mainstream in the cloud by 2030. But this Chinese strategy has raised concerns in the US. Some American politicians fear that Chinese companies will use RISC-V to bypass export controls or reduce their exposure to future restrictions. The logic is understandable. If China no longer depends on ARM or x86, then future sanctions become far less effective. Some members of Congress have even proposed limiting U.S. participation in RISC-V International. But here lies an interesting paradox. RISC-V is already public and open source. It cannot be closed off or controlled. Limiting U.S. participation would mean surrendering influence over future standards, and U.S. companies would lose competitiveness against Chinese firms. It's no coincidence that RISC-V International moved its headquarters from California to Switzerland in 2020. This strategic move ensures neutrality and shields the organization from geopolitical pressure by any single country, guaranteeing global access without geographic restrictions. It's the same strategy used by organizations like the Internet Engineering Task Force or the World Wide Web Consortium. There's a deep irony in this situation. RISC-V was born in the U.S., developed at UC Berkeley with American funding and guided by David Patterson, a legendary figure in American computer science. It's supported by U.S. companies like Google, Intel, and NVIDIA. And yet, due to geopolitical tensions, it's becoming increasingly global and possibly slipping out of American control. If the U.S. decided to limit its participation in RISC-V, the consequences could be counterproductive. American companies might be forced to use less efficient technologies or pay expensive license fees. Startups might relocate abroad to access RISC-V, and a competitive edge would be handed over to Chinese companies. This situation echoes the early days of Linux. Some governments were skeptical about an operating system controlled by international developers, but those who embraced Linux, like Google, Amazon, and Red Hat, thrived, while those who resisted early on lost market share. The future of RISC-V hinges on one fundamental choice: global collaboration or geopolitical fragmentation. In the first scenario, RISC-V remains a truly open standard where the US and China compete within the same ecosystem, accelerating innovation. In the second, we risk geopolitical forks of RISC-V, duplicated efforts, and a slowdown in global innovation. What's at stake isn't just chips, it's who controls the computational infrastructure of the future. RISC-V could be the last chance for a truly global and open standard in an era of rising tensions. The question is, Will we be wise enough to preserve this opportunity? Understand how crucial and globally important this project has become. It could reshape the tech landscape, define the roads ahead, and it's open source. While geopolitical tensions create challenges, there's another side of the story that shows how strategic RISC-V has become for global innovation. And that's particularly evident in the massive investments pouring in from around the world. The European Union, for example, put a staggering 270 million euros on the table in 2023. This wasn't just general funding, but a very specific framework partnership agreement aimed at supporting a single company capable of driving a RISC-V CPU development project targeted at supercomputers, servers, and data centers. The message is clear. Europe sees RISC-V as a path to technological sovereignty in the high-performance computing sector. But it's not just about public investment. The private sector is moving major pieces into place. Nordic Semiconductor, known for its wireless chips, has done something extraordinary. It brought together some of the biggest names in the semiconductor industry. We're talking about Robert Bosch, Qualcomm Technologies, NXP Semiconductors, and Infineon Technologies. Together, they created Quintoris GmbH, a company whose sole purpose is to promote the global adoption of RISC-V by developing next-generation hardware. Think about that. These aren't niche players. They're industrial giants moving billions of dollars. The fact that they've decided to collaborate so closely on RISC-V says everything about the direction the industry is heading. This is no longer about betting on an emerging technology. It's about positioning themselves to dominate the next computing paradigm. Market figures back up this trend. RISC-V International forecasts that the market for RISC-V IP and software will reach $1.7 billion by 2025. That may seem modest compared to today's tech giants, but let's not forget, we're talking about an architecture that's only 14 years old and has reached commercial maturity only in the past 3 to 4 years. But RISC-V represents far more than just an alternative to existing proprietary architectures. It is the embodiment of an entirely different vision of how innovation should work in the digital era. It's a vision of a future where hardware innovation is no longer constrained by expensive licenses or proprietary restrictions imposed by a few large corporations. This vision is built on a few key pillars that are already changing the rules of the game. First, true technological freedom. RISC-V offers something that just a few years ago seemed impossible: the ability for anyone to design advanced processors without needing permission or paying tolls to anyone. It's as if, overnight, the recipes for building car engines became public and free. Second, the acceleration of innovation driven by openness. When thousands of engineers around the world can contribute, experiment, and improve on the same technological foundation, innovation moves at an exponential pace. It's the same principle that made Linux so powerful. Distributed collaboration always beats closed development. Third, unprecedented global accessibility. Today, a university in Bangladesh, a startup in Kenya, or a research lab in Estonia can develop cutting-edge processors using the same technological base as Google or Intel. This level of technological democratization is nothing short of revolutionary. Fourth, the extraordinary synergy that's emerging with Linux. The RISC-V and Linux combination is unlocking possibilities that didn't exist before. Fully open-source systems from hardware to software, co-designed optimizations between the kernel and processor, and development ecosystems that are entirely transparent and verifiable. But it would be dishonest not to acknowledge the real challenges that still exist. The software ecosystem, though growing rapidly, is still maturing compared to ARM or x86. Many development tools are still immature, documentation is sometimes lacking, and the developer experience can be less polished than on established platforms. However, when you look at the big picture, RISC-V is proving something fundamental: that open source can work in hardware too, a domain traditionally closed and proprietary. It's no longer a question of if RISC-V will succeed, but rather when it will reach critical mass and how fast it will transform the industry. The 270 million euro investment from Europe, industrial alliances like Quintoris, and market forecasts nearing $1 billion, all these signs point in the same direction. We are witnessing a paradigm shift, that could be just as impactful as what Linux brought to software. The next time you hear about a revolutionary new chip, a self-driving car with extraordinary computing capabilities, or an IoT device doing things that seemed impossible yesterday, don't be surprised if you find out that under the hood, there's RISC-V. The open-source revolution in processors has not only begun, it's accelerating, and it promises to completely rewrite the rules of the hardware world. Thanks for watching.